Done a lot of Bode, but today we're going to talk about Bode. So we're going to start with first order Bode plots, then we're going to go to how to use it, what does it mean, and then second off, we'll do second order. So what we've talked about last time was like, hey, if I know what my transfer function is and I know my frequency that we're inputting into the system, we can figure out the magnitude and the phase. But that's just looking at one frequency. I can do it 10 times at different frequencies, but that can get time consuming. It's not as helpful. So we can actually create the two plots of these based on the transfer function. So we're going to plot them versus a range of input frequency. These two plots are called a Bode diagram. H.W. Bode, part of LaBelle Labs back in the 30s. LaBelle Labs? Yeah? Or just Bell Labs, whatever. Now, again, magnitude and phase, those are the two things we need to fill in that equation, right? That we were looking at last time. I just need amplitude ratio, phase angle. Those are the two plots we're going to plot over a whole range of frequencies. But to fit it well, these are on a log scale. So amplitude ratio is plotted in decibels. The frequency is on a log scale. I'll show that to you. But this is on the equation sheet. So let's say I have a magnitude here. If I want to plot it on the Bode plot, we're going to take 20 log of that. So that's log base 10. So that's one thing. As I look at these diagrams, it is plotted in decibels. So this is the conversion. Go back and forth. If I have decibels, I divide it by 20, then take, we'll get to that, but 10 to the power. Okay, so this is on the equation sheet. This is important for what we're working with. Some background on this. So 20 log of 1. Let's say my amplitude ratio is 1. Magnitude is equal to 1. Both of the amplitudes are the same. 20 log of 1 is equal to 0 decibels. Therefore, that's our unity amplitude ratio. Any amplitude ratio greater than 1 results in decibels greater than 0. Anything less than 1, we go less than 0 for decibels. So very small amplitude ratios equal large negative decibel magnitudes. For example, if, let's say, my amplitude ratio or magnitude is 0.124, what is the magnitude in decibels? Technically, yes. I don't know if you can do this in your head, by the way. What's 20 log of 0.124? I'm going to calculate this out. Negative 18.1 decibels. It is technically less than 1. It's actually less than 0. It's actually less than negative 17. This is our magnitude in decibels. So for us to be able to see it, and this is an important part, because if I was just looking, if I didn't turn it into decibels, the plots are going to be all over the place. But by using a log scale, we're able to really see the full output of the system over a nice range of frequencies. So that's why the log scale is used. Now, here's an example of a first order Bode plot. Then we'll talk about how it can be constructed, like what makes sense. So first off, Bode plot, always a pack of 2. It's always magnitude and phase. Okay? Both of them, as you can see, have frequency on the x-axis, and that is a log scale. What is 10 to the negative 1? 0.1. 10 to the 0, 1. Then we have 10, then we have 100. Notice it's not, this is our log increment, so this goes 10, 20, 30, 40, up to 100. That's the log scale for frequency. That is in radians per second. And then for magnitude, this is in decibels. So we convert it to decibels, and then we can see basically our output amplitude is going to stay pretty consistent until we reach a certain frequency where it turns the corner. We'll talk about that. This is the same graph basically for every first order system. It's just our starting point and our frequencies will shift depending on the transfer function. And then lastly, we have our phase angle that goes from 0 to a larger negative number. So here's some stuff from a lot of this is written on the equation sheet. So I'll just go through some of these different rules. This is basically the basics of how a first order Bode plot is constructed. First, there's a flat low frequency asymptote, that's like our boundary line. Exists with the magnitude of 20 log K, where K is the DC gain. Do you remember how to find the DC gain? So you have the transfer function, the S is equals 0, that's my DC gain. So we can find that, and that's like our flat line right there that we're gonna follow. Next up, we're going to look at the high frequency line. This exists with a slope of negative 20 decibels per decade. What does that mean? Well, it's going to drop 20 decibels, that's the y-axis, over 1 decade, that's on the x-axis. Decade means like I'm going from 10 to 100 radians per second, or 4 to 40 radians per second. That would be a decade. Basically times 10. So we've got this line, we've got this line. Where do they match up? Well, where they match up is they intersect at the corner frequency. So the corner frequency is equal to 1 over tau. That's radians per second. Tau is time constant. So a lot of, like we know about DC gain, we know about the time constant. This is where those two lines are going to intersect. This is the corner frequency. This is where that magnitude turns the corner based on tau, how quickly it responds to inputs. Now, for a first order Bode plot, the phase angle starts at 0 and then approaches negative 90 at higher frequencies. But the corner frequency is also used for part 5. The phase angle hits the halfway point when we're at the corner frequency. So that's the corner frequency tells us a lot of information, both phase angle, halfway point, and magnitude where it turns the corner. And on the equation sheet, we have a standard form. This is really related to the standard form that we were already looking at for first order, just the input-output equation. This is our transfer function. We want to match up this. So it looks similar to that, where we get tau s plus 1 here. Therefore, whatever's my numerator, that is my DC gain. Because when this goes to 0, I'm left with k over 1. So that's our DC gain right here. And once I have it in the standard form, we can find the corner frequency. We can find the starting point, 20 log k. And that's how we can construct the Bode plot. Exciting? Questions? So You don't have to write this down. I'm just going to do a quick example of this. Let's say that we had a transfer function and we get it in the standard form. So we get 1.5 over 0.25s plus 1. Therefore, tau is a quarter of a second. That's my tau. And k is equal to 1.5. Now, if I was doing the method we were talking about last time, I take this transfer function, I change the s's to omega i's, and what we can do is, well, we can plug in different omegas here to see how that affects the magnitude and the phase. And so the equations would look something like this, where I'm finding the magnitude, I'm finding the phase angle, and all of them are, well, both of them are based on the frequency. So as frequency is low compared to when frequency is high, that's where we see a large change in the phase angle and magnitude. So what we could do is we could plug in a bunch of different frequencies. So we've got this table here. Let's say from those two equations, we plug in 0.1, and we plug in 0.5, and we work our way all the way up to 100 radians per second. This is what happens to the magnitude. So at really low frequencies, our magnitude is essentially the DC gain, right? 1.5. That's what our DC gain is. So we stay close to 1.5 until we hit a certain point, and then it really tapers off for our magnitude. That means that our output amplitude really drops. And then, let's see, this converts it to decibels, so that's 20 log of this number. So we can see it's pretty consistent, and then it drops off pretty fast. That's what's going on. Now, if we did the phase angle, again, as I plug in that omega, I start close to 0, and then once we get to those higher frequencies, I get close to negative 90 degrees. So this is what the graph would look like. So again, I've changed it to decibels here. This is my frequency. Where do these lines meet? Well, the corner frequency is 1 over tau. Tau is equal to 0.25, or a quarter of a second. So 1 over that gives me 4. If I go back to the table, this is my corner frequency. What do you notice about this line? Look at the phase angle. What's the phase angle at it? Negative 45. This is where we hit the halfway point for the phase angle, how far it's trailing behind. But this is also kind of that, again, this is called the corner frequency because this is where that magnitude does turn the corner pretty drastically. And so we can see that when we plot all those different points, that 4 is the point where these two lines meet. This is my 20 log K, which is 1.5. This has a slope of negative 20 decibels per decade. So from 4 to 40, we drop 20 decibels. And then our phase angle starts at 0, hits the halfway point at the corner frequency, and then goes to negative 90. Every single first order system, I guess you can flip something, but has a similar feel where it's just a straight line and then another straight line, and the corner frequency is where that all takes place. How do you find the corner frequency? From the transfer function? What? 1 over tau. So once you find tau, you can find the corner frequency. Yes. Yes, yes. Okay. Now in MATLAB, I want you to pull up MATLAB if you got it. Just MATLAB. Now on the MATLAB code sheet in Halo, it has these 4 lines of code. We've already done the first 3 before in creating a transfer function, but the last line is the important one. We can create, if I get a transfer function, we can create the Bode plot just by using Bode of system. And so this is the same Bode plot for that transfer function. We can see it starts at a little bit over 3 decibels. And then where does this thing transition? Well, it's at 4 radians per second. That's where we hit the halfway point here. And that's where these 2 lines meet up. So we can see the corner frequency equal to 4. It should work, especially if we have all the toolboxes, I think, that we've already worked with. We'll talk a little bit about why this is important as we get closer, but again, you know, if I'm trying to wonder what the output amplitude is or the phase angle at any frequency, if I don't want to run 20 tests, but I kind of know how my system is set up, we can plot this to see, you know, what's our output going to look like at any certain frequency. So we can try to tune that in. Does it work? Cool. All right. So that's a helpful tool. We're going to look at second order soon. It looks a little bit different than this, so some of the rules change when we reach a higher order. But so what I'd like you to do, we have a transfer function here. Now you can use the equation sheet. You can pull it up on Halo. At the bottom, it's all stuff about Bode plots. We're doing the first order equation. I want you to calculate some of these things. I want you to try to just do a really quick sketch of like, what does this look like? You want to find the corner frequency. You want to find the starting point, 20 log K. But do you know how to? I've already gone through some of the important equations. They're up here, right here. Once you have it in standard form, can you figure out what is this graph going to look like? So I'll give you some time to work on this, and then we'll see. Once you're done, once you kind of have an idea of what it's going to look like, then you can plot it in MATLAB and just double check that it makes sense. What is 20 log of 2? 6.02. So 6.02 decibels. That's going to be our starting point for the magnitude. That's where that horizontal line is going to be. That's our starting point, 6.02 decibels. Now, where is it going to turn the corner with a slope of negative 20 decibels per decade? That's going to be 1 over tau. So once I have it in standard form, 0.083 or 1/12, that's my tau. So 1 over that gives me 12 radians per second. So that's our corner frequency. And that is where those two asymptotes will meet. That's also where the phase angle will hit the halfway point. So that gives us information for both the magnitude and the phase. So we can really easily sketch this out like, hey, I know where some of the starting point is. I just have a log scale. And then we can double check it in MATLAB. And does anyone put this into MATLAB? When I put it into MATLAB, it gives me a plot like this. So we can double check a little bit about what's going on. I know that my starting point is 6 decibels. Great. Now, when it comes to the corner frequency, here's 10, here's 100. So that means this is 10, 20. So 12 is somewhere in here. And that's where this hits the halfway point. That's also where these two lines meet. So this is our corner frequency of 12. So just be careful with log scales. It's not 10, 11, 12, right? This is 10, 20, 30, 40. They're not nice, even breaks. So 1, 2, it gets almost halfway between 10 and 20 on the log scale. That's how we can kind of double check ourselves. Our next goal is, well, let's say I'm given a Bode plot. Let's say I don't even know what the system is. Can we actually find, magnitude? Can we find phase from it? Yeah, I just need to look at what our frequency is, because both of these are based on frequency, looking at on the x-axis. Questions? This is a first order Bode plot. We'll get to more complicated second orders. There's a little bit more going on, but we'll stick with this until we take a break. All right. Next up, how to use it. Hey, we're almost fully covered as far as what we're going for. So from the transfer function, we can find frequency response, all that. But I can also, from the transfer function, just find the Bode plot. Like, where's our starting point? That's what we just did. Where's the cutoff frequency or the corner frequency? This gives us information for like the whole range of frequencies. So we can either go for an exact one, this one. Our next goal is to, well, let's say I'm given a Bode plot. Can I actually find the frequency response from? And the answer is yes. So if I have a Bode plot, I should be able to find at that frequency what our response will be. So suppose I have a system. I don't know, I guess this is our transfer function. So it's 6 over s plus 4 or whatever. That creates this Bode plot, so we can have that in MATLAB. In fact, you know what? You've got MATLAB pulled up. Let's plug that back in. 6 over s plus 4. That's our transfer function. So instead of doing the sinusoidal transfer function and having to solve for magnitude and phase, we're just going to let MATLAB plot this Bode plot for us. Okay, now what I want to figure out is if the input is 7 sine 2t, what will our outputs be? So I have a system that responds differently at different frequencies. So we could plug in any number of frequencies in here. But our goal is to, let's say I kind of know what my input is. How will our system respond? What output will we have? Any ideas of where we should start? Well, no one answered. The system will respond based on the input frequency. What is the input frequency? 2. It is 2. So what we should first do is look at 2. So 10 to the 0 is 1. This is 1, 2. So this is our radians per second. That's based on the input. So in MATLAB, you should be able to actually pick a point. If we can find 2, we can find what that magnitude is, so we can really pinpoint that number. We can also find what the phase is. So in the MATLAB graph, if I can find frequency of 2, we should be able to find the magnitude is 2.55. That's our value in decibels. Now, this is in decibels, so this is in a log scale. I cannot just find the output amplitude using that. So this is equal to 20 log, not necessarily of k, but 20 log of our actual amplitude ratio or magnitude. So I know the decibel value. I want to find this. What's our magnitude? Not in decibels, just unitless. How do we go backwards from here? How do I find this? First, I divide both sides by 20. And then how do I get rid of the log, base 10? I know you know. You know, right? Not e, because that would be natural log, but it's 10 to the power. So to find the actual amplitude ratio, we're going to take that 2.5527 first, divide it by 20, and then we take 10 to that power. And that's how we cancel it. That's how we get rid of the log. And so this is our actual amplitude ratio when we take it out of decibel form, 1.3416. This is our magnitude. We're going to use that. That's the important thing, because this is on a log scale. We do have to convert out of there. The other part that we need is the phase angle. So again, in MATLAB, you can click when you find that frequency. We can find the phase angle that's negative 26 degrees. Do I like degrees in my final frequency response equation? No, I don't. So we're going to want to change the phase to radians, which we just multiply this by pi over 180 to get to radians. And so that would be our phase in radians. So what this number is, this is the magnitude or amplitude ratio times the input amplitude, which is 7. So that means that my output is going to have an amplitude of 9.3. We still have the same frequency, and then here's our phase angle in radians. This is how we can find the frequency response using Bode plot. Questions? A lot of the problems come out just from conversion, making sure we take stuff out of decibel, phase to radians. But anytime I want to use a Bode plot, I have to know what my frequency is. That's the major thing. I'm just looking at that certain frequency. What is my magnitude and phase? Okay. So we're going to do this problem, and then we'll take a break and then cover second order after the break. Okay, this is example 9.6 from the textbook, which you're all so familiar with. You read all the time. The input voltage is sinusoidal. It has an amplitude of 2.4 volts. We have an R and a C value. We want to use the Bode plot to find the input frequency, omega, where the magnitude of the output voltage drops to 1.2 volts, or where it is half of the input. What should we do? What do we start with? Obviously, they want me to create a Bode plot. How can we create a Bode plot? Let's create a transfer function. Great idea. So we got to do some Bode. We can take a breath. What is the order of the system? It's first order. So this is going to be a first. Oh, that makes sense. We were just talking about first order Bode plots. I've got my diagram here. So we have a current. We have a sinusoidal voltage. Input, output. Obviously, the input is En, and the output is E sub C, the capacitor voltage, which is our output voltage. So we now have the option of solving this. We can either use impedance to do it, we can use our traditional KVL, KCL. I don't care which method you want. Should we take a vote as to which one we should do? Or just one per, what would you like to do? Impedance? Great. No? You want the other? What? You think it'll be easier? Depends on your level of comfort with both, but what would you like? Stalemate right here. Shoot. Well, I don't really care which one. Should we have a 5-minute dialogue? Figure it out. Okay. We can use our. I haven't. Yeah, you're right. We've done a lot more impedance lately, so maybe we go back to the other stuff. So let's do a KVL. KVL, we have EN is equal to ER plus EC. Okay. So this is equal to RI. And I could say that this current is affected by the capacitor. And on our equation sheet, I sub C is equal to C dot. And so we can say EN is equal to C, RC EC dot plus EC. So if I turn this into the S domain, we can take that dot by current. So we plug that in here. Now dot becomes S, so we can combine these two capacitor voltages together. And therefore, EC over EN is equal to 1 over RCS plus 1. Maybe that was easier. Okay, so this is our transfer function. It is first order. Now, they gave us some values here. So R is equal to 4 ohms, C is 0.003. So we can plug that in. There's our transfer function. So what is K? Are we in standard form? Just in standard form? It is. I have the 1 right there. That's something S plus 1. So K is just whatever the numerator is. K is equal to 1, which means that at low frequencies, the output is going to equal the input amplitude. So at low frequencies, the amplitude ratio is 1. But obviously, as we increase frequency, we'll see it dip down. Tau is equal to 0.012. Which means that this system reaches steady state within about 0.05 seconds. That's 4 times tau. Okay. Now, just by having this, obviously we could plot this by hand. But if I plot it by hand, I don't know if I'm going to find quite the right answer. So what we want to do is we want to take, you've already got it pulled up in MATLAB. I want to plug this into MATLAB. This is my transfer function. we want to determine the place where the output voltage drops to half of the input. So we're going to plug this into MATLAB, and our goal is to find that frequency. You got it? You got the Bode plot? But now what are we looking for? This is the Bode plot for this system, for this RC circuit. But what does it tell us? So our goal is to find the frequency where EC is equal to 1.2 volts. En amplitude is 2.4 volts. Where's this going to be? We have our two amplitudes. So what amplitude ratio are we looking for? What magnitude are we looking for? We're trying to find a magnitude which is equal to output amplitude over input amplitude, or we can say EC over EN. We're trying to find the amplitude ratio of 0.5. Now, if you look on MATLAB, do we have a magnitude of 0.5 somewhere? What? It starts at 0 and it just goes negative? That's crazy. Sure you plugged it in right? Because what did we forget to do? I forget. What is the y-axis of the magnitude Bode plot? Decibels. What I first need to do is, okay, now that I know I'm looking for a frequency where my output is half of the input, that means amplitude ratio of 0.5. 20 log of 0.5 is got to be some kind of negative number. So we're doing it right now. It is about the same, isn't it? That's crazy. So we got 20 log of 0.5 is negative 6 decibels. Now I want you to look on that Bode plot. I want you to pick around and try to find that frequency. What frequency corresponds with negative 6.02? Because if that's what I'm trying to go for, I'm going to try to set my voltage source to have that frequency. Because, oh yeah, a little bit under 150, maybe 142 or something like that. Yeah, so you can kind of pick around and you can zoom in. Sometimes it's a little bit difficult. There's more code on the code sheet where you can actually plug in a certain frequency. It'll tell you the magnitude and phase, but our goal is to try to find something close to that. And so this is what we have. So there's the Bode plot. So we already calculated, we're looking at negative 6 decibels. So at negative 6 decibels, if I drop down to negative 6, that's about 144 radians per second. And That would be the frequency that we're trying to run at. Now, what we see from this Bode plot, and you've probably heard of this before, this is a low pass filter. So this orientation is going to cut out any high frequency. So based on whatever that resistor is and capacitor, anything basically over, where we're at, the corner frequency is 83 radians per second, but anything above that is going to be cut out. It drops pretty quickly. We don't really get any output at higher frequencies. By the way, this corner frequency is equal to 1 over tau. So we found tau was 0.012. That's how we found the cutoff corner frequency of 83.3. So we're higher than that when it comes to getting half magnitude. That's our low pass filter. I have a little bit more about this because we've done stuff, especially in instrumentation, with different types of filters. But the goal of the filter is to cut out high frequencies. Now, the way these are constructed is we can adjust where this cutoff frequency or where the corner frequency is. So that's what this next part is about. For example, let's say I have the same circuit. We already have it modeled. Let's say that the input voltage is noisy. So we have our main signal here, which has a low frequency. So then we also have a noisy signal, which has a really high frequency. We don't want that. What does this do to it? Well, in Simulink, we can kind of put them together. So I've got my main signal here. I've got my noise signal. So it's a combination of that. Here's our noisy input. It goes through our low pass filter, and then we get our output signal. And so this is what the voltage looks like going in. We've got our main signal, but we see there's a lot of noise, right? We got that 800 frequency noise. It's kind of bouncing around. We don't really like it. So what does the filter do? Well, after it goes through the filter, this is what our output looks like. So it takes all that noise and deletes it. It's gone. So what we're left with is a clean signal. Now, we do notice the amplitude is pretty close. It is a slight phase behind. So by using the filter, and we can look at the Bode plot in the next slide, it is going to shift it a little bit by taking that noise out. It's going to delay it a couple milliseconds. But we now have a clean signal thanks to just one resistor and one capacitor. So why is that? Because if I'm looking at the Bode plot, here's my 10 radians per second clean signal right here, the main signal we're looking at. Here's my noise. And so the noise, we see basically no amplitude out of there. It's gone. It's wiped out. Whereas this one, we keep a good magnitude, so our amplitude stays the same, but we are delayed a little bit. So our phase angle is about -7 degrees. So that's kind of cool, being able to see what a Bode plot can do. So if, like, I'm able to take a transfer function and create the Bode plot, we can see what frequencies pass through, which ones get cut out, and where does that transition happen. That's going to be the corner frequency. One of the classes is just awestruck. It's so awesome. All right, good? Great. Couple last things before we take a break. How can we shift this? Well, if I'm just shifting in the y-axis, what changes that is K. So if we have a higher DC gain, my graph is going to start higher. Like at output, we get a pretty high output. That's a large K. So K is what shifts it up and down on the magnitude. When it comes to where the frequency is, that's all based on tau. So if I have a high tau, that's going to shift it to the right. If I have a low tau, it's going to shift it to the left. And we see that also affects the phase angle, right? That's going to shift along with the magnitude. So really the two things for first order is DC gain K and the tau, the time constant. That's affecting where these graphs are. So like for that example of the RC circuit, how would I shift if I want to cut off other frequencies? I can change my resistor value. That changes my tau. And so then I can cut out different frequencies. So choosing those two things will help you be able to cut off different frequencies. All right, let's take 5. It is 8:06, so at 8:11, we're gonna continue with second order systems, and then be done sometime. Coming down, Scooby. Thanks. Oh, wow. My brother-in-law is into like synchronicity, where like no, it's like where everyone's like thinking like if you do something, someone else does the same thing. Like we're all connected in that way. Yeah, it's kind of interesting. He's also gone out. I think he's not a flat earther anymore. He also used to think that airplanes don't actually fly, even though he's been on an airplane. Like I don't know what. The airplane doesn't actually move. But yeah, we don't know. You can't trust any of those videos, or even just watching at the airport. Those might just be screens, not windows. All right. So I'll start another channel on my YouTube. If you're into conspiracy theories, we can talk more. But today our last topic is second order Bode diagrams, which are slightly different than first order. First off, let's start with the standard form. Now, this is again very related to the standard form we have covered for input-output equations. Notice we have a damping ratio, we have a natural frequency. So you don't necessarily have to write down the rest. We won't really be using it, but the standard form is on the equation sheet. You always want to put it in standard form. And then we'll talk about what that means for the Bode plot. But for example, if I have this in standard form, we can see that the DC gain is equal to 1, right? If I set all the S's equal to 0. So therefore, my starting point on the log scale would be 0 decibels if it is at unity. Okay. Here's some rules. Well, first, let's take a look at this. This is the second order Bode plot. What's the difference here? There's a bump. The second order system, especially if they're underdamped, will have a bump on the magnitude line. Yes. And so we'll talk about that. That applies resonant frequency. So we still have the same starting point, 20 log K. We usually see some kind of bump, and then it actually dies out a lot faster. So it's negative 40 decibels per decade. So it does drop off after that point significantly quickly. The phase angle, you might notice, also changes. It goes from 0 to negative 180. So we can go a full pi out of phase instead of pi over 2 for a first order. So we'll talk about a little bit of this. Let me go back to this. So here's some of the rules. Same starting point as a first order. Once I find K, we find the decibel. That's our starting point. And then we have an asymptote with a negative 40 decibel per decade line. those two meet at the corner frequency. And for a second order system, corner frequency is just natural frequency. So once I find that, that's where those two lines meet. As for the bump, the peak magnitude increases as the damping ratio is decreased. So very low damping means we're going to have a very high peak amplitude on that magnitude line. We'll talk about once this reaches basically 0.7, if my damping ratio is 0.7, that's where we see like almost no bump. So we have a high amount of damping. It's going to look more like a first order. The phase angle, again, goes from 0 to negative 180. And we'll talk about how that kind of affects the slope. But the phase angle hits the halfway point, negative 90 degrees, when we're at the corner frequency or natural frequency. So that's also a similar rule. It's just obviously our scale is doubled. So we're going to hit the halfway point at the corner frequency. So we can see here again, if my corner frequency is 10 compared to 100, this is where I hit my halfway point, negative 90. This is also the same point as where those two lines intersect. And in the case of this transfer function, I have very low damping, so that's why we see such a high bump. And that corresponds with resonant frequency, which we'll talk about. Okay. Let's talk a little bit more. So this is just kind of representing what happens as damping increases. So if I have low damping, I have a high bump, and I have a quick transition for the phase angle. The more damping we have, if we have more friction in the system, if we have more of that, what we're going to do is we're going to bring this resonant frequency down. We're going to smooth it out, and we're also smoothing the phase angle, so it's less of a harsh transition. And so there's a point where once I hit basically 0.7 or √2/2, that's where it looks like a first order system. I don't see any bump. I don't have a resonant frequency. So the more damping you have, you can avoid some of that, any kind of peak in the magnitude. But I'm going to let this MATLAB guy talk a little bit, and then we'll talk about
or it will spin up or down the frequency.
even like seeing how there's usually some point we didn't know. It's just like the whole place, right? Like the sound is it's the dark, or if you go up and lower to that's where I can see dark. So there's a lot of different cases where, whoops, I didn't have this on here, but resonance is where we see that high amplitude, and it's all really based on frequency, not so much what the amplitude of the input is. So let's talk about that resonant frequency. This is where the input frequency is near the corner frequency. Now they are not the same. Resonant frequency is slightly different than the natural frequency, and the equation's right here on the equation sheet, but down here. If I have no damping, they are the same. So if there is zero damping, that's where the resonant frequency is equal to natural frequency. The more damping we have, the more it shifts to the left on the graph. Let's see, and it's going to shift to the left. It's going to decrease. So the more damping we have, the less of a bump we're going to see. And where is that transition? So at the bottom, number 3, if damping ratio is greater than 0.7071 or square root of 2 over 2, there is no resonant peak. It looks like a first order. So with enough damping, we can essentially take out any kind of resonant frequency. We're not going to see any change really in our output amplitude. But if I want resonant frequency, that's where we want to have little damping. So a small amount of damping allows us to have that resonance. A couple other things. Cutoff frequency is defined as the maximum input frequency at which the output will track satisfactorily. So this is, again, amplitude ratio of square root of 2 over 2. This is a 3 decibel drop. So you maybe heard 3 decibels. This is, if I'm going from my starting point, we drop 3 decibels. That is called the bandwidth. I'll show you an example graph on the next slide. But basically, we're going to find what's our K value in decibels. That's our starting point. We drop 3 decibels. Where does that 3 decibels hit the Bode plot? That's like our cutoff frequency. That's where we still see a sizable output, but anything past that frequency, we're not really going to have much of an input or output. So the amplitude drops quite a bit, and the phase angle is quite large as well. So that's called the bandwidth related to the cutoff frequency. For example, if this is my Bode plot, to find the bandwidth or the cutoff frequency, I start here. So let's say DC gain is negative 36.3. We're going to drop it 3 decibels. So that's negative 39. And then we trace it to, or you use MATLAB to figure out, what is that frequency? That's our cutoff frequency. So it's not the same as the corner frequency, which is here, the natural frequency. This is where, after this point, you see my output just dies out really fast. So that's like our cutoff frequency. So a lot of filters and stuff, this is kind of how they're constructed. They're based on, if you want a cutoff frequency of this, go with this RLC circuit, can get you this kind of low pass filter. That's our cutoff frequency calculation. You just drop 3 decibels. Questions? Okay. I have some stuff on the MATLAB code sheet. We've already done Bode plot, but you can also, at a certain frequency, it can actually tell you what the magnitude and the phase are for that frequency. You can also, if you have an SSR, plot the Bode plot as well. So it can take an SSR and you can look at, you could take your SSR from lab 2. Think about this. Take your SSR from lab 2, find the Bode plot and see what kind of frequency input where we might see these masses go crazy. Kind of cool. So we can analyze, like, we tried it at 2 different currents. Well, what happens if we tried the whole range? So that Bode plot can kind of show you, like, what happens if we're able to get this frequency. We can see a really high excitation. Anyways, on your own time. How about that? Yeah, you'll do it on your own time? That'd be cool to see. I have it on my computer too. Maybe I'll try it sometime. Okay. Now, here's our rules right here. I want you to practice this a little bit. Let's say we have our transfer function. We want to find the where our starting point is, what's our corner frequency. We want to figure out what our damping ratio is, and then that's most of the key information. So I want you to try to solve for some of these, and then we're going to do a final problem together. So first put it in standard form. We want to find K, we want to find natural frequency, and find damping ratio. And from there, we can kind of piece together how this thing's going to look. What did you do first? Standard form. We get 3.5 over s squared plus 0.75 s plus 5. So yeah, putting in the standard form, now that matches our standard form equation. Couple of things. So natural frequency is square root of 5. And then we can figure out the damping ratio once I have that value. So this is 2.24 radians per second. Then we have 0.75. Divided by that, divided by 2. We get a damping ratio of 0.17, which is unitless. So my question is, will this have a bump? No bump? Okay, if this is less than 0.7 or square root of 2/2, then we will have a bump. In fact, this is a really small damping ratio. So with the small damping ratio, we're actually going to have a pretty high peak. We are going to have a resonant frequency. It's going to be sizable as far as the magnitude. So that's going to happen. Now, the other thing I need to figure out is, so natural frequency is the same thing as the corner frequency. That's where this thing turns the corner. That's where the phase angle hits the halfway point, which is -90. The other thing I need to figure out is what is K? What'd you get for K? Did anyone get a K value? 3.5? 17.5? We're getting farther away. 0.7, that's correct. Now you can, this is DC gain, by the way. So it is, I can look at that equation there, but if I set all the S is equal to 0, this is just 3.5 over 5. So instead of multiplying it by 5, divided by 5. Yeah, so that is our case. So then if we do 20 log of 0.7, this is going to be a negative number. This is going to be our starting point in decibels. Do you have what that is? 20 log? 3.2? What'd you get? Those are two different numbers. Yeah, it should be negative 3.0, 3.1. Oh, you missed the key. Okay, great. So now we have all the pieces. I know that it starts at -3. That's my starting point. I know that the cutoff, or sorry, the corner frequency is 2.24 radians per second. That's where it's going to turn the corner. It's going to have a slope of -40 decibels per decade. So it drops out pretty fast. At that corner frequency or natural frequency, it also hits, it goes from 0 to -90 and to -180. And the slope is going to be pretty high because damping is low. There's one last thing that I want to calculate. I want to calculate, because we definitely have a bump, where does that bump occur at? So this is equal to, if I have my equation, resonant frequency is equal to natural frequency. This is natural frequency 2.24 times the square root of 1 minus, what is that equation? I have it somewhere. I just don't want to mess it up. That would be 2 times zeta squared. Okay, so this is how we can calculate the resonant frequency. This is going to be less than the natural frequency. It's going to be slightly different. That's what we want to calculate. We'll do that real fast. It's probably still in the 2s because damping's pretty low. 2.17 radians per second. This is where the peak is going to occur. Okay? So if I take this transfer function and I plot it using MATLAB, we know that we start at -3. So that this is 1, this is 2. So around 2.2 is where we hit the halfway point, and that is where those two lines intersect the natural frequency. However, the peak right here, this is at the resonant frequency. So it's a little bit to the left. The more damping we would have, this would come down, but it would also shift to the left. So the resonant frequency would be a little bit more different than the natural frequency. But at this point, this is where the phase hits the halfway point. Okay, that's kind of how these second order plots work. You know, we're going to eventually do even higher order. We'll do fourth order, just like with the suspension problem. So sometimes you can have two different peaks. If I have two different masses, okay, how do we deal with that? But today is just kind of the basics of what do these things mean? How do they relate? We can obviously adjust it. You know, if I change my spring stiffness or my damping coefficient, that we can shift the graph. We can shift it to the left or right. We can shift it up and down, just like with the first order systems. Okay, so our last problem. So I have about 30 minutes to do. Between two plates. I got two plates. There's a mass in between them. These are both actually fixed. It's nice. I apply a force here. We want to find, based on these components, we want to find the resonant frequency. So first we want to find the transfer function. We want to find some of the important stuff, create a Bode plot, and then determine the steady state response for a given input. I'm going to give you some time to work on the body. Create that. Leave everything in terms of variables, B, K. But once we find that transfer function, then we want to find resonant frequency. Basically, the Bode plot, how it's going to respond to different inputs. If you have questions, ask the person next. You can, bounce ideas off the person next to you. it starts at an equilibrium. have, so once we have the transfer function, variable, plug it in, it's all positive and nothing stable. On their values, and then trying to figure out a little bit more about how the Bode plot is going to look. Also use MATLAB to back it up. Like the rock. That's great. Good. This should be our input output equation. Put in our values. That's already going to work. At 0.6. So let's get this thing. Now, after that, now we're going to try to find the result. By the end of class is part C. Try to find the steady state output for a certain input using the That will be like our last lecture. It won't be a whole lot of new stuff. Right? It is a really small number, but that just means that you have a small DC gain, so your output's going to be a lot smaller than your input. You can put it in MATLAB. Yeah, my main goal is first off, can I find all of these, and that informs how this is constructed. So you got to know how to, what they mean. How can you actually put this onto a graph, or how can you take it from a graph? So really, it's more of just understanding where stuff goes. But once I have, again, DC gain, I can just take this over that. Very small DC gain. So for any kind of input, my output is going to be sizably, it's only like 1% of it. So on the log scale in decibels, it's -38. Find the natural frequency, then we can find the damping ratio, which is a little bit higher than the one we had before. So there's going to be a little bit less of a bump. And then because of that, we do actually see a pretty decent change in the resonant frequency. It's going to be shifted over about 1 radian per second. So it's going to be to the left. Whereas natural frequency, this is the corner. This is where a lot of stuff kind of lines up. The resonant frequency is always to the left. Just depending on how much damping we have. And then this is what our graph looks like. So again, the halfway point is at the natural frequency, and that's where these two lines basically intersect. And then, yeah, unfortunately, these didn't line up. That's weird. But then this is my starting point, -38. We see we have a bump here. Now, no one's asked me yet today, but I've had larger classes than this. How do we determine the magnitude of that bump? Any ideas of how we could maybe find that? Like I know there's a bunk, but like how far up does it go? And the answer is we can use the stuff from last class. I have the transfer function. I can do a sinusoidal transfer function. I can plug in the resonant frequency, and that will give me the magnitude. So if I plug that into my sinusoidal transfer function, solve for magnitude, that would be the magnitude value. Obviously, if we have a Bode plot, we can just take it from there in MATLAB, but that's one way that we can calculate what that max peak would be on the Bode plot. All right. The last thing I want you to do, we have our Bode plot and everything. So the last couple minutes, I'm going to give you 5 minutes. I want you to take that Bode plot in MATLAB and try to solve for what would the x steady state. So what does my position output function at steady state look like for this input? That's the last thing I want you to work on. So using the MATLAB Bode plot, can you find our x steady state output? And if you have questions, if you have no idea where to start, you can ask me or the person next to you. But we want to determine what kind of output we're going to have. If I know what my input force is going to be like and the frequency that it's going to be acting, what is our output position going to look like? That's our goal. Okay, so you have your Bode plots. Yeah, sometimes it doesn't really allow you to pick it well. Now, again, there's some code in the MATLAB code sheet where you can just plug in, like you can put in the code, give me the magnitude and phase at a certain frequency, and it can give you that value. But I got somewhat close on my graph. And so, again, we're looking at 8 radians per second, because that's my input, the frequency that we're going at. So I can find my phase, negative 35 degrees. And then about negative 33.7 is our magnitude, but that is in decibels. So I got to get that out of decibels, which is taking it divided by 20 and then 10 to that power. So I found an amplitude ratio of about 0.02. We also changed the phase. We want that in terms of radians. And so once we have those two things, again, this was just like last class. Those are the two things we need to be able to solve for the frequency response. Again, this is just steady state. I don't care about what happens at the beginning at startup, just what happens at steady state. This would be our steady state. So it moves 0.04 or basically 4 centimeters is the amplitude. It has the same frequency as the input, but then we do have a phase that it's trailing behind. And the last part, if we wanted to find the bandwidth, we just have to figure out what's a 3 decibel drop. So if I go from negative 38 to negative 41, that frequency that lines up is 17.1. So this would be like the cutoff frequency. Any frequency higher than that, I don't really see much of an output. It drops off quite quickly after that. So that would be the cutoff frequency. All right, and that's basically my lecture for today. So we talked about Bode plots. There's first order, no bump. Second order can have a bump depending on the damping, and it has a resonant frequency associated with it. We'll talk about that a little bit more next class. We'll do some more problems, but that's mostly all of the main focus of this topic, looking at systems in the frequency domain. So some of your homework involves creating the Bode plots, analyzing them, trying to figure out like what's going on. So the more practice you have, the more time you give yourself, the better. That homework is not due until next week. So obviously the main focus is finishing the benchmark today. If you have questions, I have office hours today, or if you want to answer, I can answer some stuff right now as we finish class. Any questions about this? Okay, I will post these slides. So the main thing we worked on was Bode plots. These are the standard forms. And then from there, we can find our important values, be able to plot them. So we'll continue this next week, but I'm going to leave this up here. Good?